angles. How are we going to talk about angles? Okay, well, first off, the definition of an angle. An angle consists of two rays, different rays, with a common endpoint. All right, so we have the ray DC that begins at D, goes through D, and continues. We have the ray DE that begins at D, passes through E, and continues. So an angle then just keeps on going because it's composed of rays. It doesn't just stop right here unless it's part of it is a line segment, like in a triangle or something. Okay, so how are we going to talk about this? Let's see. We can talk about the sides of the triangle, the sides of the angle. This is a side. This also is a side. And here is the vertex. So the point's called the vertex, and each of the two rays, the parts of them, are called the sides. Something else we can say about it. This is inside the triangle. I keep saying triangle, sorry. This is inside the angle. This is outside the angle. This is also outside the angle. So that's one way to talk about it. We can say, we can also, the interior of the angle, it's okay to say it that way. The exterior of the angle, it's okay to say it that way. Okay, well, what if we measure this angle? We take a protractor and we measure it. And I measure from here to here, and that's 50 degrees. I can mark it that way. I might put the arc mark, and it's not essential that I do when I do this. I could just put the number 50 in degrees here. That would be okay too. How are we going to name this fella here? Okay, well, you got to remember when you name an angle, it's like you put your pencil down and you trace it. You must name it the way your pencil moves as you move over the angle. So I'll start up here and I go C, D, E. So how do I name it? I can name it as angle C, D, E. Okay, well, what if I look at it the other direction? I come along here, I go come along here, I go E, D, C. Is that just as good? Yeah, that's just as good. This is a mark that means the angle. Either one of those are just fine. It doesn't matter which one we call it. Notice the obvious, and that is the vertex is always the center. So it makes it a little bit easier to spot if you happen to notice that obvious thing. Now for this particular angle, there's only one angle here, one angle that we're talking about anyway, and the vertex is at D. So I can also refer to this particular one as angle D by the vertex itself. Okay. Well, if I want to talk about how big it is, this is angle D. How big is angle D? Now, this is kind of cumbersome to talk about how big it is. What we're going to say is that the measure, M for measure, of angle D, or CDE, or EDC, doesn't matter. The measure of angle D is 50 degrees. That's a number. The measure, the measure will be a number, 50. Okay? So the measure of it is 50 degrees. That's how we say it. We don't say angle D equals 50 degrees because that's going to be the shape of it. Okay, see the shape here? We call angle D or angle CDE or angle EDC, okay? But we want to know how big it is. We'll say I'm looking for a number, and it's the measure of it, generally made with the protractor, okay? All right, next up, what if we take our same angle, CDE, but now we add in one on the interior of the angle. this point X is on the interior of the angle CDE or EDC. Trace it along as you go and you'll get it right. And I've drawn another ray from D through E. From D through X. And it is interior to it. So we now say that the point X is interior and that the ray dx is interior. Okay, a couple of things happen when we do this. Okay, this original angle, this is the same one. Remember that this original angle was 50 degrees, right? It's still 50 degrees, but now it goes all the way from there to there. So I need to draw this arc like this to show that I'm talking about the whole thing. So I put a 50 degrees there. It's right next to this arc, and I know that means I mean the whole angle. I don't just mean part of it. If we look at it and we measure, we'll see that this is 30 degrees and this is 20 degrees. Now I'm not going to put those little angle marks right there because it would make it look like I was saying they're equal, and they're not. They're one's 20 and one's 30. So you'll get a feel of how to do that. Okay, so now this original angle, that's the same one I just had. It was 50 degrees. I put in a ray interior to the angle through the point X, which is interior to the angle. It formed two angles, 30 and 20 degrees, out of the 50 degrees. Okay, so how are we going to name this now? Okay, notice that you cannot say angle D anymore. Not allowed. The reason for that is there are at least three angles at angle D. The 50, the 20, and the 30. So once we have more than one angle at a vertex, we have to use all three letters. So now to name this, we will say angle C, D, X, or it can be backwards with D in the middle, angle X, D, E, or it can be backwards with D in the middle. And then the double one, the big one, is angle C, D, E. Notice each time again, this little common thing that will help you to remember that the vertex is always the middle one. You can say them frontwards or backwards, it doesn't matter. But now, since there's more than one angle at this vertex, you have to say all three letters. Now actually, there's another angle at this vertex. It goes around this way. That angle. So see, actually there's a fourth one there. We hardly ever talk about it, and if we're going to talk about it, we'll say, I mean that one outside. If I don't say I mean the out one outside, then I don't mean it. This is called reflexive. It's a reflexive angle. Since I'm pretty sure you already know there's 360 degrees in a circle, we can subtract the 50 and find out that this one is 310 degrees. So, unless I say, or unless somebody says that they mean the reflexive angle, we're just going to ignore it. We won't count it, we won't think about it, and we know it's there, and it's a nice angle, but we're just not going to pay much attention to it unless specific attention is drawn to it. Alright, next up, what if we have two angles? Okay, I have two angles here, and they're identical. Well, no, they're not. They're named different, and one's red and one's blue, so identical and the same. But what I mean is, they're both 40 degrees. Okay? Now, if I wanted, I could also put a mark there and one mark there. One arc, because they are congruent. But I've already marked that they're 40 degrees, so I'm not going to do that. Okay, so I can call this angle CDE, or angle EDC, or I can just say angle D. And you know what? Saying angle D is easier than saying all those letters. So I'm just going to say angle D. This is angle D and its shape. And then I would say that the measure of angle D is 40 degrees. And down here, the measure of angle G is also 40 degrees. So now then, okay, this is a number, right? 40, and the units are degrees. So when I say that the measure of angle D is the same as the measure of angle G, since that's a number that I've measured, I will say equals. You'll recall I use equals when it's something that's a number. Here we are measuring. It's a measure, and the result is a number. So that means, oh, Ollie, hush. Ooh, big thunderbuster, both the doggies did. They're coming and getting under the chair, poor doggies. Okay, so the measure of angle D is the same as the measure of angle G. It's a number, so we use equal. Okay, so that's talking about measuring the angle. Let's talk about the shape. Hi there, blue angle D. You're just real shapely like angle there. You look nice. Oh, angle G. Nice, pretty red angle. You look really nice too. You know what? I'm pretty sure y'all are the same shape. You're blue, you're red, but you're the same shape. So when we look at the shape and we're comparing the shape, I will say that angle D is congruent to angle G. Okay? Congruent, we recall, means same size, same shape. It's composed of two symbols, the similar, which means same shape, and equals, which means same size. In some books, you'll see this with only one line. That's still congruent. Okay. But most of them these days use that one. Same size, same shape. So angles that have the same measure are congruent. That's how we're talking about it. Again, we're talking about the shape. Okay, now it's not as big a deal now when we're talking about an angle, because I mean an angle doesn't have a whole lot of shape, you know. But when we get it, it's got more shape than just a line or a point. But hey, that's what we're talking about here. So when we're talking about the shape, we'll say congruent, same size, same shape. When we're looking at it and saying it's the same, we'll say congruent. When we're talking about something that we measure, we will say equals. All right, these things you should already know. Write them down just to reinforce it, please, because that's a good thing to do. The definitions. An acute angle is an angle less than 90. Right is exactly 90. Obtuse is between 90 and 180. And this one is really odd. A straight angle. Oh, give me a break. 180 degrees. Duh, it's a line. It's a line. Okay? All right. But there are some times when we need to think about it as an angle, and if we do, we'll give in and we'll call it 180 degrees. But you know what? That's a line. It's not an angle. Okay. I guess it is two rays going in the opposite direction, two opposite rays. But nevertheless, 180 degrees. Reflexive is anything between 180 and 360. Please make a note of these things. Okay, let's go back to the angle that we just had here. Remember we had CDE, and we put an angle, a ray on the interior that divided into two angles, not equal ones, a 30 and a 20, and we noticed that the total was 50. This can bear a little bit more contemplation. One of the things that we're doing, particularly here early in geometry, is we're looking at the obvious, analyzing it, stepping back from it, thinking about how we can use it. So this is one of those opportunities to actually be purposeful about how we're doing this. Yeah, 20 and 30 is 50, right? What did we just do? We just added two shapes together. Whoever said you can add a shape together? Well, you can. Okay? And so here, with the one we had, 20 and 30 makes 50. You remember how we did it? We did it by adding an array. What did we just learn here? We learned the overarching principle that the whole is the sum of the parts. And we have a postulate for that, and the postulate is angle addition postulate, which we'll be using a whole lot. Okay, so make a note of this in your notes, please. Angle addition. All right, next up, we're going to talk about measuring these angles. How are we going to measure an angle? Well, I can make a protractor. Let's see. Here's a line. A protractor is measuring angles, right? So at one angle, we know, we'll talk about it more, but we know that one line is 180 degrees. Half of it's going to be 90. So if I will place on this my angle, so for example, if I have a ray going out here and a ray going out here, I can number and find out how big that is. Remember how I can make a ruler, I can use a ruler? Well, I can make a protractor. It's a pretty crooked looking protractor, but you'll get the idea. So if then this is at 40 degrees, if I go 10, 20, 30, 40, let's say that this is at 40. So just like on the ruler, I measured out equal units. I'm now measuring out or making marks in about every 10 degrees, 50, 60, 70, 80, 90, 110, 120. We'll say that that one is at 120. Okay, and then 140, 160, oops. Okay, 180, that's a big one. We'll pretend it's equal, okay. 20, 130, 140, 160, 170, 180, that's what our problem was. Okay, so this would get it down to 180, and then this would be 0. Okay, it's still not a very good protractor, but you get the idea. I can make a protractor. I can draw a half circle, and I can measure off in roughly equal units and use that to measure. Now, how will I use that to measure it? Okay, here's my angle I want to measure. I can see that the red ray from the angle is at 40 degrees. The blue one is at 120 degrees. So now, guess what? I can use a protractor to find out that my angle is 80 degrees. Isn't that clever? Oh, who'd have thought about it? You know what? I'm thinking that sounds like a postulate. Indeed it does. It is the protractor postulate. I can make a protractor. I can use a protractor. Go ahead and copy down this stuff. Write down at least the main points. Make kind of a drawing. Maybe you can make one a little bit better than mine was. And put in things that tell you value about it. For example, I can make a protractor. I can start at 0 and number to 180 in equal portions. I can use a protractor by noticing the measure, the angle measure of each one of my items, and I can tell the difference. So I can measure just the angle from here. I can measure the angle, the blue-red angle. I can measure those all along. You know, I just said that it was 180, just like, you know, it was always 180. Did it ever occur to you to think about why it's 180? Let's think about that. While we're thinking about it, let's just kind of stare at the night sky here. Okay. Think back to the days of long, long ago when folks didn't have MTV, they didn't have this, they didn't have that. What did they have? Well, at nighttime it was dark. They might lie out on the ground and watch the stars. In about 300 years, BC, whichever one you want to call it, about 300, a guy named Euclid Euclid, lived in northern Africa in Alexandria. And he, like a lot of mathematicians, thought it was interesting to look at the patterns in the sky. So he'd just lie out, look at how they change from day to day. He and others would mark, like they'd see a particular bright star, Sirius or something. I'm not that good at the name of stars, but they'd see maybe a particular constellation. They'd name the constellations. Maybe they'd see Pisces. And they'd notice every morning when the sun went up, or every afternoon when the sun went down, and then they could see the stars, but it was at a slightly different place. And these guys would say, like, it moves. It's not always in the same place. And then they started drawing charts of the stars. And they said, and over years they would draw charts of the stars and then compare their charts of the stars. And they figured out that every day it was about the same difference in the stars across the middle of the sky. They were a little close. Actually, they were very much similar to the distance from the equator as us, so it would be similar for us. So they started marking off the stars. Every day it moved this much. And then they'd check it next year, see if it's about the same, and it's about the same. And then the next day it moves this much, and then check it off, and they do about the same. And they thought there was probably about 360 days in the year. They did not have the precision of instruments that we have. And so they decided they'd go with 360 days in the year. And you know what? We can be really glad that they did. I'll tell you why in a minute. And so they marked off the sky, called the ecliptic, into 360 equal times, equal portions for one day. Okay, for one day, it's this much different than it was yesterday. And then the next day, it's the same amount. And they noticed it's about the same amount difference as they drew out the patterns in the stars. And so they used 360. Now, why are we glad that they used 360? We're glad that they used 360 because 360 has a whole lot of factors. It'll divide by 2, it'll divide by 3, it'll divide by 6, it'll divide by 4 and 12, and all kinds of numbers. That makes it really easy to do geometry. Imagine if they had known that there was approximately 365 1/4 days in the year. How much harder geometry would be. Okay, yes, I know. The Earth has slowed down a little bit in the past 2 millennia, but not enough to make that much difference. Okay, so that's where it comes from. So if you're ever tempted to forget one or the other, there's about 360 days in a year, and there are, by definition, 360 degrees in a circle. So in case you were inclined to wonder where it came from, that's where it came from. Those mathematicians lying out on their back, staring at the stars, got that for us. Okay, more about back to angles. Let's formally state the definition of an angle, of congruent angle, congruent, remember that means congruent. Whoa, you can't see that. There we go. The definition of congruent angles is angles that have the same measure. Now again, we're talking about shape, not the numbers, but if numbers are the same, then we call the angles congruent. An angle bisector, we did some of this with folding, and we'll do it by other construction. That is, an angle bisector is a ray that divides an angle into 2 congruent angles. So here we have the big angle in green, and in red is the bisector. It's marked with an arc that has the same number of arcs, like a 1 and a 1. That means these are equal in measure, which means that this is an angle bisector. Okay, let's work a problem that might help, that might come up with something like this. So what if we were to have this? Okay, there's my diagram. And I know that the measure of ADC, okay, I got to trace it. ADC, okay, that's the big one, is 85 degrees. I want the measure of BDC. Trace it, B, D, C. Okay, the bottom one's the one I want. Well, how am I going to get it? Well, the angle addition postulate tells us I can add them together to get the big one. The sum of the parts is the whole. So I'm going to add the parts together. I'm going to say that the measure of angle ADB plus the measure of angle BDC is equal to, okay, measure, it's a number, so I say equal, I don't say congruent, okay, is equal to the measure of angle ADC. Okay, well, let's look at the drawing here. ADB, ADB, okay, that's 4x minus 7 degrees, plus BDC, BDC, 5x plus 2, equals ADC, okay, that's in the directions there, so that's 85 degrees. Okay, you might look at this, oh, that's degrees, what am I doing, what am I doing, I'm sorry, okay, degrees. So, we're talking about the numbers and working with the numbers, so this is just algebra, and we don't have to put the units in until we're done, just like any other algebra. So since we don't need to put the units, we can just write this more simply as this. And truth be told, depending upon how it looks to you, you don't even have to write this step if you don't want to, but sometimes it's helpful to make sure that you get everything in the right place. Okay, from here it's just algebra combined by like terms. 9x minus 5 equals 85, 9x equals 90, x equals 10. Okay, so the answer is x equals 10. No. The answer is not x equals 10 because that wasn't the question. The question is, what is the measure of this bottom one here? Okay, so the measure of angle BDC equals 5x plus 2. Okay, I know x is 10. 5 times 10 plus 2 equals 52. Okay. Well, that looks pretty good. You know, let's make sure. What about this angle up here? What about the top one up here? The measure of that one, that's ADB, and that's 4x minus 7. So if 10, that would be 40 minus 7, which equals 33. Okay, so what I have here, I checked over here to make sure I was right, and then I look at the two. The answer that I'm looking for is that BDC is equal to 52, but to make sure it was right, I went ahead and did the other angle just in case, and when I see I add those together, I do in fact get 85. So I got it right. Okay? So that's good. It's nice to get something right ever so often. If you would, please work these problems. Pause your playback here and work them, and then I'm going to put the answers up for you. Okay, pause it. And here's the answers. Okay? Make sure you can work it to get these answers. Okay. And when you've done that, here into the lesson.